Okay, we're going to talk a little bit about matrix determinants now. So this will be the next section on linear algebra. So matrix determinants. Focus this hopefully. All right. This pen's a little bit, I think it might be running out of ink, so I'll use another one. Okay, so determinants are a characteristic of square matrices, and if the idea here is it serves as a test for if a matrix has an inverse. I mean, at least for our purposes. There's other reasons there's other things that a determinant represents, but the idea here is that for some matrix A, right? The determinant of A is equal to 0 if and only if A is not invertible. So A inverse doesn't exist. So finding a matrix inverse is not the easiest thing to do. So the one thing you might want to do before you embark on finding a matrix inverse is to test whether or not the determinant of that matrix is 0. If it's 0, you might want to stop right there and say, right, this matrix is not invertible. Maybe some of the columns are linear combinations of the other. Maybe there's a 0 row. So there's all sorts of reasons why, but all right. It's worthy. It's a test it's good to run. It's good practice to do. All right. So the determinant of A, we usually symbolize that with like the absolute. It almost looks like the absolute value sign. So that would tell me that's how we call. That's what we symbolize the determinant of A as. All right. And if A is just some constant, so if this is the matrix A, it's just a single element, then the determinant of A is just equal to that constant. So for example, if we got the matrix 2, just like in the notes, that's the matrix there, the determinant of this is just 2. All right. For a 2 by 2 case, so 2 by 2 matrix, so let's say A is given by our typical A, B, C, D entries. The formula is you're going to multiply across the diagonal and then subtract across the off entries. So the determinant of A in this case is going to be equal to A times D minus B times C. Right? So if we have our matrix 1, 2, 3, 4, then the determinant of that matrix, let's call it A, is equal to 1 times 4, which is 4, minus 2 times 3, which is 6, and that's equal to negative 2. It's not equal to 0, so that tells us this matrix actually has an inverse, right? So we can actually define the inverse for a 2 by 2 matrix. That's an easy case. So A inverse for a 2 by 2 matrix A is defined as 1 over the determinant of A times. Now here's you just have to memorize this, but for now. But we're going to swap the diagonal entries. So there's going to be a D up here and an A down here. And then we're going to multiply the off diagonal entries with a negative 1. So that's going to be negative b and negative c. All right. So then going back to our 1, 2, 3, 4 matrix, we already know what the determinant is. So we can do this 1, 2, 3, 4 inverse is just going to be 1 over negative 2 times. So again, we have to swap the diagonal entries. So we put a 4 up there and a 1 there, and we multiply the off diagonal entries by negative 1. So it's negative 2, that's negative 3, and then this becomes the following matrix. Let's see. That's negative 2. This is positive 1. That is positive 3 halves. And then negative 1 half. Can we test this? Absolutely. So all we need to do is multiply by that original matrix, and if we did our work right, we should get the identity matrix back. 1, 2, 3, 4. All right. So we have negative 2 plus 3 is 1. We have negative 4 plus 4 is 0. We have 3 halves minus 3 halves is 0. And then 3 minus 2 is 1. So this actually checks out. All right. Pretty nifty. So you just have to literally memorize this formula for a 2 by 2 matrix for now. Until we learn the formula for the 3 by 3 and above, then you can apply it to a 2 by 2. But for now, it's pretty easy. Just remember, it's 1 over the determinant times this thing called the adjoint of the matrix, which for a 2 by 2 is you swap the diagonal elements, and then you multiply the off diagonals by negative 1. All right. So here's a real quick proof that we can perform on here. So let's just go ahead and take this matrix here and multiply it by the ADBC matrix. And turn this a little bit here so you see what I mean. So we're going to have, let me get my black pen again. So 1 over the determinant of A is 1 over AD minus BC. And then we have D here, minus B, negative C, and then positive A. And then we're going to have our original, let me do this in a different color so that we can differentiate the two of them. We have our original matrix, which says A, B, C, D in the entries. All right. So let's start off by multiplying these. I mean, we can do whatever we want, but easiest thing, let's just start by multiplying these matrices out. So that's just going to be 1 over AD minus BC times, so we have D times A minus, D times A plus negative BC, so minus B times C. Then we have B times D minus B times D. And then for the bottom, we have negative A times C plus A times C. And negative B times C plus A times D. All right. And now look what happens when we then turn around and multiply through. This just becomes, right? See that? It's AD minus BC divided by AD minus BC. Again, when you have a scalar out front, you multiply all the entries by that scalar. So this becomes the number 1. Right? B times D minus B times D is 0. So that's automatically going to be 0. And then here, negative AC plus AC is also 0. And then look, this is A times D minus B times C. So that becomes 1. And that's it in a nutshell right there. All right. So this formula works. It's a good one to have on the back of your hand, so to speak. All right. So now let's move on to a bit of a more complicated topic, and that is a generalized recursive formula for the determinant of any square matrix A. And this is going to get a little hairy. And I'll probably make a mistake, I'm sure, so bear with me here. All right. So we have to start with this definition of something called matrix minor. So the minors of matrix A we can symbolize that as M subscript I, comma J. Those are just going to be the determinant of A after row I and column J are deleted. Come up with an example here. All right, so let's do a 3 by 3, and I'll just do 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm hoping this is, I'm hoping it's invertible, but I just spammed that out there. So let's see, what would be M, I don't know, 2, comma 3, right? So what we would have to do is follow the directions. We want to delete row I and column J. So we need to delete row I. So we're going to delete row 2, right? And we're going to delete column 3, right? So what's the determinant of this matrix here? 1, 2, 7, 8, right? Because that's what's left over. We deleted that row and we deleted that column. So what's left over is this becomes 8 minus 14 or negative 6, right? So that is the answer to, sorry. Lost my train of thought. That's the answer to the minor in the 2, 3 position for matrix A. All right, so just keep that in mind. We need to apply that to any, because we need to go all the way across this matrix and do this across one of those rows. All right. So, okay, so that's our minors. Definition number 1. All right, definition number 2. Now that we know what the minors are, we need what are called the cofactors of A. So the cofactors of A, let's see, cofactors of matrix A all right, are the signed minors. I know what you all are thinking. Can this get any more ridiculous? And it can. All right, so what do we mean by signed minors? So let me define the cofactor. It's going to be similar. It's going to be C, comma, I, J, and that's going to be negative 1 to the I plus J power, oh boy, times minor I, J. Wait a second to close the door because my okay, so going back to that, let's say M23, what would then what would C23 be then? All right. So it would be negative 1. Whoops. I don't know why I did that. Negative 1 to the 2 plus 3 power times negative 6. All right? So what's negative 1 to the 5th power? It's easy. If negative 1 is to a positive power, if negative 1 is to an even power, it's a positive 1. And if negative 1 is to an odd power, it's negative 1. So this is just simply going to be negative 1 times negative 6, which is just equal to 6. So that's what the cofactor here is. It's going to be C of 2, 3 is going to actually be positive 6. So we have to make sure that we know what the sign is when we're doing the cofactors, because for the 3 by 3 case, the matrix, which again, if you remember what I called it, the adjoint matrix, is going to be a matrix of cofactors, right? So we have essentially the determinant of A. So let's say A is equal to just some generalized n by n matrix. So A11, A1n. So we don't know how many of these elements are there. We don't know how many rows are there, but we know there's n of them, right? A(n) by n. Then the determinant of A is equal to, again, we have to sum over some row. So here j equals 1, some column, and all the way to n, a, I, comma, j times the cofactor of that, right? So we essentially, so what does this say? We essentially need to choose one of these rows, and we need to expand across that row. We can also expand across columns if you want. All right? But let's focus on rows here. So let's do the example. So we want to, this is a little bit arbitrary. It'll make a lot more sense if we actually do an example of this. So let's say A is actually equal to the following matrix, which is 1, 0, 2. Whoops. So let's make that a 1, 0, 2, 3, 4, 6, and 5, 4, 10. All right. So I am going to let's choose row 1. So I'm going to go across row 1. So I is equal to 1 here, and we need to sum up over j all the cofactors. So how do we do the cofactors? Again, you have to remember it's going to be so the determinant of A then is going to equal, we have to sum, so we have to take the actual element in the first entry times the cofactor of that first entry. The element of the second entry times the cofactor of that second entry, plus the element of the third entry times the cofactor of that third entry. So we're summing here. All right, so let's do the first one. So what's A11? It's just equal to the number 1. What's the cofactor? It's going to be the signed minor, which again is when we remove, let's see if I can do this here. We need to find the determinant of that right there, all right? And that looks to me to be, it's the following here, so it's going to be 4, 6, 4, 10, right? And then we add we have to do the next cofactor. But again, what's a cofactor? It's a signed minor. So here, this is entry 1, 2. So I is equal to 1, j is equal to 2. We have to multiply that by a negative 1. So this is going to be negative 0. So it's going to be plus a negative 0 times the determinant of, again, we have to get rid of that column and the top row. So it's 3, 6, 5, 10. All right. And then we need to do the cofactor here, right? So it's going to be plus, because again, this is going to be entry 1, comma 3. And 1 plus 3 is 4. Negative 1 to the 4th power is positive 1. So we don't need to subtract that. And then we need to get rid of first row, last column. It's 3, 4, 5, 4. Okay. All right, so that's equal to, let's see, 40 minus 48. Plus 0, because anything times 0 is 0. All right, plus we have here 12 minus 20. All right, what does that all equal? 40 minus 48 is negative 8. Plus 12 minus 20 is, hold on a minute. 40 minus, oh. Why did I think this was 48? This is 40 minus 24, folks. I'm having problems, right? 40 minus 24. I'm sure some of you were probably yelling at your computer. Sorry about that. So this is 40 minus 24, which is equal to 16. And then here we have plus 12 minus 20. Times, oh, we forgot to put the 2 there. Don't forget, we need that aij. Don't forget to put that in there. So it should be a plus 2. So it should be plus 2 times that. And that's going to give us minus 16. We get 0. Oof. We have a 0 determinant, which tells us that this matrix does not have an inverse. So why does this matrix not have an inverse? Any takers on that? Let's take a look at column 1 and column 3. They're linear combinations of each other, right? If I take column 1 and multiply it by 2, I get column 3. That's why we don't have a matrix inverse here. But wanted to go through the hoopla of doing that matrix inverse for you. All right. Let's do another one that might have an inverse. How about we do this one that we started off with, right? Let's give that a try. It might take a little bit, but let's give it a try. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. I want to find the determinant of that matrix. Let's go ahead and expand across the top row. I mean, we can go up the middle column if we want. In fact, why not? Let's do the middle column. So this is going to be, let's see, this is in position 3, 2, right? So that's going to be a negative 1. So it's going to be negative 8 times the determinant of 1, 3, 4, 6. And again, how did I get that? I got rid of this column here, and I got rid of the bottom row. And what's left over is 1, 3, 4, 6. Okay. And then here, this is the second row, second entry. 2 plus 2 is 4. That's an even number, so this is going to be positive. So it's going to be plus 5 times the determinant of 1, 3, 7, 9. All right. And then this entry here is the 1, comma 2 entry. So that's 1 plus 2 is 3. That's a negative. So it's going to be minus 2 times the determinant of 4, 6, 7, 9. Again, that's from deleting those 2 there. All right. Okay, so let's do this here. So that's equal to negative 8 times 6 make sure I do this math right. 6 minus 12, all right, plus 5 times 9 minus 21, minus 2 times 4 times 9 is 36, minus 42. I think I did this right. We'll see. So that equals negative 8 times negative 6 plus 5 times, let's see, 9 minus 21. Let's see if I can do that in my head. Negative 12? No. 9 minus 21. It's got to be negative 12, right? Yeah, negative 12. Minus 2 times, what's 36 minus 42? It's negative 6. All right. And we get 48 minus 60 plus 12. And that equals, oh my God. I can't catch a break here. That's equal to 0. So this does not have a, I guess this does not have an inverse. Let me double check this. I'll double check it later, but if I did everything correctly, it looks like the determinant is 0, which tells us that this is non-invertible. Nothing glares at me right off the bat, but there's got to be a reason anyways. So, interesting case there. All right. Okay. So we can go, as the notes say, we can go up any row or any column. I just demonstrated that by going up this column here. But we can go across the middle. We can go. So typically what you want, a tip is you want to find a row with a lot of zeros in it or a column with a lot of zeros and expand up that row or that column because it saves you a lot of time because those zeros are going to drop off a lot of those cofactors, a lot of the cofactor multiplication, so you won't have to worry about that. All right. There's a couple of rules in the notes that you're going to want to go over, and let's go ahead and end the video there because the next video is going to cover matrix inverses in general. Right. So this was determinants in general. So go ahead and practice a couple of these, and then the next step is going to be to use this formulation, especially with the cofactors and determinant, to actually calculate the matrix inverse for any large matrix, all right, greater than 2 by 2. Okie dokie. Again, any questions, reach out to me via email. Bye now.